So there we are, chaos. So the first 2/3 of the book, for somebody like me, were very boring, but necessary because you have to learn how to do pizzicatas first before you can play an instrument. And the really interesting thing happened in 19th century, but nobody understood that it happened. It was only in the mind of Henri Poincaré. In a very mathematical way and without any pictures. It happened again a number of times. For example, Dame Cartwright in 1945 plotted the first strange attractor and described it. But it took only until the age of cheap computations where physicists' children could buy Commodore or some other programmable computer with 64K memory that some of these ideas became humanly accessible to everybody because they're very visual. And in 1963, Edward Lorenz whittled down equations for weather from billions and millions to 3 coupled Fourier modes, which he gave names X, Y, and Z, their coefficients, their strength of 3 oscillations in flat Earth, heated by sun with atmosphere going through convective motions. And this happens often, I would say almost always in nonlinear problems, is that some set of steps brought you to some equation. It's written in a way Newton and Leibniz were written it in terms of infinitesimal variations of your state variables, let's say temperature, pressure, humidity, whatever, being compensated or being described by some credible set of linear or nonlinear functions. In these very simple examples that tend to be multinomials. So they're linear terms, they're products of them, and there's some parameters. And in your particular physical or biological problem, you have some notion what these parameters are, but for our purposes, it's largely irrelevant. So we analyze this equation in the way we're taught how to analyze it in the boring part, of course, 1 and 2 dimensions. Dimensions are so constrained, then very few things can happen. But when you get to 3 dimensions, the chaos breaks loose, and that's the rest of this course. The way Lorenz decided to pursue it, he was incredibly lucky because he had access to a computer and he was at a rich research institution, so he had staff members who knew how to compute. And this is sort of not the first, but one of the first very important non-military applications of computation, modern computations. You looked at equilibria. In this case, they're very easy to understand. And there were 3 equilibria which were all unstable. One of them happened to be the origin, the usual equilibrium of death. All fields have strength 0. And there are kind of things that happen in 3 dimensions that didn't happen before. The equilibrium of mixed stability. So these 2 had a complex pair of eigenvalues, which means there was a rotation. That rotation can be either a circle, spiral in, spiral out. They are unstable, so it turned out to be rotation, spiral out. But then it has a 3rd eigenvalue, which goes in, a stable one. And what that meant is that if you start at someplace, so one natural way to start is start at this unstable equilibrium. This one was very easy. It sits on an invariant subspace. So if you start on the z-axis, you stay on z-axis and you exponentially decay into this equilibrium from either side. So you can remove that one. then even though it's 3 dimensions, you don't have to solve cubic equation when you're looking at the characteristic equation of 3 by 3 matrix. 2 by 2 suffices. And that had one direction that went in the plane, and there was another one that went out. And you start out in XY plane, but Z is an active variable. You're excited, so you fly off from XY plane up, it turns out, toward these two equilibria. They look attractive to you because they actually have a stable direction. So they're pulling you in like sirens, pulling Hercules in, not Hercules, but Odysseus. And you fly toward them, you plop close to one of the equilibria. If you went on the other end, you would go on to this one. This has two repelling directions. And then it turns out you stay in a plane close to this unstable equilibrium, and it's unstable, but not very. It just kind of pushes it a little bit out. So you rotate and you spiral out and you spiral out and you spiral out and you spiral out. And at some point, you can't spiral out more because there is this z-axis. And if you're too far away, the other equilibrium, it's also stable, known as it known. So at some point, you fly across and you plop close to the other equilibrium, but it's unstable. It's actually just a mirror image of us, so you already know everything about its instability. You go unstable, you go unstable. So you're going away. You keep doing this until you've gotten too far away. And then you have to go by this z-axis, which is just a line in 3 dimensions. It's an invariant subspace. If you're in it, you stay in it. That means if you're outside of it, you cannot get in. You can approach it, but you can't get it. But you feel its presence by being pushed down and then thrown away close to this unstable manifold. And in Lorenz's and the 2 women who helped him do the calculations, simulations, this seemed to go on. Now, the next thing you do as applied mathematician, you say, well, it's not dying to an equilibrium. Well, then it must go to a limit cycle. But you can show there is no attractive periodic orbit, what these guys like to call limit cycle. So you're unwanted. If you start far away, we found out that any little volume contracts to something that's smaller than 3 dimensions. I was very excited about that last week for reasons I'm sure still don't appreciate. You fall in, so you know that globally you can't go very far. There is a global attractor, meaning, if I start with very violent motions of weather, the friction will damp it and I'll go from very crazy state to something that falls in here. We know this because we looked at the time average of the divergence, our 3-dimensional state space flow, and we found it to be negative. So we found out that whatever this falls in must be smaller than 3-dimensional volume. It's not a point, which is 0-dimensional. It's not a 1-dimensional thing, like a periodic orbit, which is a curve of 1 dimension. It turns out not to be 2-dimensional thing. You might imagine there's some bagel someplace and you run on the surface of the bagel. So what do? You're unwanted. Everywhere you go, you think, this looks like I'm falling into an attractive point. I get close, I get kicked away, spun away. What is this? Maybe I could end up here. You get close, it turns out you can't even get close. It's so unstable, you just get kicked away. So that's a paradox of deterministic chaos. The law is totally precise. You must follow it. But there is no peace, there is no rest. Wherever you go, you get kicked around, and you do this forever. And in some sense, we're used to it, because when you think of ideal gases like argon molecules hitting each other, we know that they don't stop. The whole thing doesn't freeze. So they're doing something. We know that configuration is never the same. So invent statistical mechanics, and you say, well, in principle, I could know what happens, but it is Avogadro number of different balls hitting each other. So let's follow Boltzmann and do both things called statistical mechanics. But this is only 3 degrees of freedom. So what do? You try various things. And an interesting thing about new subjects, something like quantum mechanics, nobody understands more or less, but nobody thinks, because they're kind of bludgeoned into successes of the theory. But in nonlinear science, you actually understand what you're doing often. And you try to use your ideas, and you keep rediscovering same things over and over. The Lorentz was 2 things at the same time. He was a weatherman where chaos rules, and he was a mathematician where order rules, student of the main mathematician of chaos or ergodicity to the first half of 20th century. So he actually thought in a way that we are very grateful for today, because it's a time saver. So he did first what you always do if you don't know anything. In his case, computer was spewing out numbers, 6-digit numbers on strip of paper. He and the helpers thought, well, it's a strip of paper that's called time, and it's giving me 3 numbers, X, Y, and Z. So look, what do these numbers do? So he looked at coordinate Y, right, one of the 3 coordinates, and what it did is it oscillated. And then every so often oscillations would go big, and then it would jump to negative value, oscillate. Then it would jump to positive value, oscillate. Jump to the negative value. Okay, so there's some result. So they stopped for a day, came back next day, restarted the computer with same initial conditions, ran it, and what do you know? They got a different sequences of flips between oscillations. So the thing was not just irregular looking, that's easy to have, it's irregular. But it was unpredictable in the sense that you said, well, there is some frequency here, short one. High frequency, short wavelength. But then I can just count when does this thing flip, and I should get some understandable sequencing. But no, this sequence flipped on and on and on. It never settled. Into a periodic motion. Never. You could say, well, his computer has only 6 digits. It was round off errors. But now, thanks to Wolfram, I can compute with 160, 200,000 digits of precision. Doesn't help, this whole thing continues like this. So now, what is this? It looks regular, but it's irregular and it's irreproducible. He decided to see what's the effect of making small errors in initial conditions, not in computation, but just how you start. and discovered the local instability, which I've already spent several, like 2 or 3 lectures, entire lectures discussing, because it is so important. And the idea of local instability is, we have already discussed it, that if you look at a trajectory field or observable or thing that you're measuring that you call X, which you started with some initial condition at time equals 0. And for each initial condition, you got a different trajectory, but deterministic, well known. And then you started the same thing, maybe 1% of your number away, initial number, x0. Study how it evolves in time t. And after a while, you discover that no matter how close you're in the beginning, after a while, the thing goes away, and the distance at time t, which was dx0 at time 0, grows. And how does it grow? So you plot it in various ways. It wasn't linear growth. So he and other people at other times looked at the magnitude of the vector here in 3 dimensions, but it could be in million dimensions. He knew that at time t0, it has certain magnitude, the number he said to be 0, small. But it looked like numerically that it was growing exponentially. And this Greek lambda is called lambda because Lyapunov in 19th century might have discovered it, interested in stability of solar system using Poincaré's method. The way this works, if you want to publish this in some rag like PhysRev letters, you plot it. That makes referees very happy. And you write 0 here, 10 minus 1, 10 minus 2. And let's say you're really good and you start at 10 minus 15, which you can do nowadays. So you start with a very small error. So it's logarithm. You have to go 15 digits, decimal digits, until there is a first non-zero digit. And you let this thing run. And what it does is it kind of oscillates. It's the same frequency as this. So there's something going on that cares about the short frequency. And it oscillates, but it gets bigger, bigger, bigger with time. And then there is some time where you totally lose it. And the distance you're measuring is of order 1 if system has size 1. And that is called Lyapunov time. At least I call it that. Strogats call it horizon time. No clue what horizon, but anyway. And now, if you're very skilled, you run some program that draws a line through this. And that's a linear width, so it's proportional to t. There's a number, that's this Lyapunov exponent. So that says that if I start with some very small imperfection in my initial conditions, now 10 to the minus 15 is a very small number, so almost impossible to set up experimentally in any situation, but let's say you were so good. Then as time goes, you get to the time where the error is of order 1, so its logarithm is 0. So you have a condition, logarithm. By the way, I should mention, this number being positive means that error grows, right? An unstable orbit trajectory has positive Lyapunov exponent. It's called exponent because it's an exponent of exponentials. So now you want to find time Lyapunov when the left-hand side is 0. So take logarithm of both sides. Left-hand side will give you 0 at that time. On the right-hand side, I'll get logarithm of my initial condition. Exponential of logarithm of exponential is just exponent. So I'll get lambda times t. And the sum of this thing should be 0. So I put this guy on that side. I write t Lyapunov. And I divide both sides by lambda. And I get an estimate. How long can an unstable system be tracked? What is the time at which I lose my prediction of power of prediction, even though I know the laws that govern the system to infinite precision? And you learn the painful lesson. Exponentials, which is now the word that a citizen of this country might know. Exponentials, you cannot beat them. You better join them. There is no way to be exponentials. And this is as good an example as any. So we find out that time of having accurate prediction is proportional to logarithm of my precision. For example, if I had 15-digit precision, my original number was, x of delta was 10 to the minus 15, the distance between these two guys, there'll be minus 15. And then there is a rate, and that's where the law of nature comes in. You don't control the rate, the bankers don't control the rate, the government doesn't control the rate. It's a consequence of Lorentz equations, and there is nothing you can do about it. And because this is a small number, you have minus here to make time positive. So suppose you do a realistic experiment. So suppose your error is 10 to the minus 2. Then this is 2 divided by lambda. So you see the meaning of lambda is what always rate means in exponential. This is a lifetime or typical time of exponential process. So this is, a unit. If you change units of time, this is measured in second, but if you do it in femtosecond, this might be 1. So now you say, okay, let me, I have a grad student, doesn't know what to do with his time. So let's compute this 10 times better. Chris works for a couple of years, sets up an experiment, and the error in plain QUET initial conditions is amazing. It's not 1% accuracy, but 1 part in 1,000. And, try to do that. You have to be very skillful. What do you get? Well, logarithm of 1 over 1,000 is 3. So here goes one page here. Then you say, well, we are the government and we don't want Japanese, Chinese, whoever, the Afghanistan, whoever we don't like at the moment. We don't want them to be faster than us. So we'll make a very expensive computer called, femtaflop or something, which is 1,000,000 times better, million, or experiment, but that, good luck with that won't be able to. So that means that I'm looking at delta x0 control of initial condition, which is 10 to the minus 8, 6 digits here, and voila. Well, I had a prediction for 3 seconds, now I have a prediction for 8 seconds, and I've spent million to some power dollars more to do it. So I'm sorry, if you have exponential, you cannot beat it by idiocy. That doesn't work. you have to find other ways to deal with. So you cannot predict weather. You might have scoffed at Lorentz because you said, well, 3 equations, no computing power, that's useless. What did this guy do? He discovered a conceptual limit. It said if something is imperfect, it blows at your exponential rate. And there is nothing you can do with million dimensions or anything. All you'll be able to do to predict weather to 5 days, and that's it. But if you're thinking, you can predict climate over 100 years, not 5 days. So that's, what this course is about. You have to realize what you're up to, and you have to decide what is it that matters and what you have to compute. And the person who did this first in weather, Hellman, got Nobel Prize for it. Again, so for something as childish as Lorentz's model, but conceptually important, it turns out, and that's what we have to understand, this is too hard to really get into in what we're doing right now. We'll set the stage. Even though the thing can be wild, the long-term prediction can be very, very robust and smooth. And that's a big surprise. So now we are almost ready to say, what do we mean with this word chaos? It's one of those things. I have a colleague still alive who is good in giving names that one can repeat on television. So he gave name to something totally boring about chaotic, what we call chaotic now, chaos. Now, educated people call it ergodic theory and, try to sell that on television. But chaos, everybody understands. And it's actually reasonably honest. I mean, the chaos in our world has more to do to it than just deterministic laws, but it's an important part. So what is it about chaos? Well, you can run. And you can run away, so you can have positive Lyapunov for your trajectory. You're locally unstable. And this by now we understand. There's some very nice trick we learned, but basically in a neighborhood, for a law that's not too kinky, but sensible and smooth, it's enough to look at the linear behavior in a neighborhood. That has to do with matrices, eigenvalues, and you can describe very precisely what it means to be locally unstable. So that's number one. Chaos requires local instability, but you cannot hide, or as we technically say, you cannot escape. When we're in one of the situations that we started with today, saying that I can fall into something, but I cannot leave, it means that I'm forced to do same kind of motions over and over again because, I tried to run away, I jumped over there, but then I was forced to jump back and I have to do the same stuff over and over. And that's the main thing about dynamical systems that exhibit chaos. They're interesting, number one, because they're very neurotic and unstable, everything falls apart. But once you've gone away, doesn't mean that you're done, because you're pushed back globally. And if you were in some region of state space, and there was an unstable region, then you find out that there are trajectories that, leave and then they come back. They get pushed off by the walls that forbid you to do things that are too well. There are other trajectories that leave, do a little dance, come back. There's still other trajectories that leave, do a more complicated dance, and come back. And each one of them has its own character and signature. They're distinct. They're not the same thing. So there are very many ways. There's only one way to be happy, but there are very many ways to be unhappy and run away. And that turns out to be the second component of chaos. You have to count the number of ways of returning. And that's much more sophisticated notion than a local instability. It's sort of familiar from statistical physics. The way they think about in statistical physics, they count the different arrangements of components of a system, let's say little magnets in an array, etc. And each one of them is called distinct component because, I can give it a name, I can then look at it. And as the time increases and you're more and more unstable, the number of ways you can come back also increases, also exponentially. And that I cannot argue very persuasively at this point. So you have to take a logarithm of number of ways of returning, geometrically distinct. They're global. I go along the whole space and come back. And the same thing as before, I have to take a logarithm because their number grows exponentially. I have to divide them by some number, but a different number now, which has a different name. This number is called entropy. That comes from statistical mechanics, but it's exactly what we're writing here. It's a logarithm of number of returns or number of states for exploration size of the system, or in this case, time. So you have to divide this by time. And that pulls out a number. And now, what is chaos? So chaos in determinism means that as I go around, I remain unstable. So I have a positive characterization of stability, which was this Lyapunov exponent, this thing here. If it's negative, I just fall in, but if it's positive, I run away. So I need positive Lyapunov. And if I have exponential number of ways of coming back, bouncing around and coming back in different ways, then I also get positive entropy. That is chaos. So remember, now the book mumbles because we're really not ready to understand the entropy yet. Pretty soon will be, but not quite yet. But chaos is a global thing. This is how I run across everything that's global, and local thing, how I escape. And they have to exactly balance each other in a way that can be made precise. And when that happens, my dynamical system is chaotic. So it's not enough, it's unstable. I also have to describe how it rebuilds itself.